Alright, so this video aims to give a little insight into how the nucleus of the atom was discovered. It's called the Rutherford gold foil experiment. It's also known as the Geiger-Marsden experiment, which tells us how the discovery of the nucleus of the atom occurred. Here's the setup of the experiment. There was an apparatus with radioactive material in it emitting alpha particles, and this blue line is showing the alpha particle beam. It was being shot through a very thin piece of gold foil, and around the gold foil was a detector that would light up whenever an alpha particle hit it. So by allowing alpha particles to go through the little hole in the detector and through the gold foil, they could see specifically the path that the alpha particles were taking as they went through the gold foil by where the alpha particles hit the detector. And most of the time it went straight through, once in a while deflected, and once in a great while actually deflected backwards. So let's take a closer look at what's going on inside the gold foil, what the alpha particles are doing as they're passing through the gold foil, and what Rutherford was thinking about how the alpha particles were interacting with the gold foil. So we'll take a close-up view. So the green dots representing the alpha particles, and here's the gold foil. We know in our current model that there is a tiny part of the gold foil that has the positive charge. That's the nucleus, and most of it is empty space. But that's radically different than what Rutherford thought the structure of the gold foil was. The prevailing model of the atom was that it was a solid ball of positive charge, and there were electrons spread evenly throughout the ball due to the negative repulsions. So he thought that the alpha particles would just go straight through. Now, I find this to be very troubling, because why on earth would Rutherford think that the alpha particle would go through a solid bit of material? It makes no sense until you think about what did he actually know before doing this experiment. Well, he had already won his Nobel Prize a couple years before this. The Nobel Prize was won for his work on radioactivity. And so what he knew about the alpha particle, the radioactivity coming out of the box, was that the alpha particle was very massive. It was incredibly dense, number one. Number two, it was going at very high speeds, close to the speed of light. And number three, it was positively charged. So by comparison, the gold foil was far less dense. And so by shooting this very dense, very high speed particle at a much less dense, very thin gold foil, he had no reason to suspect that anything would happen but for the particles to just go straight through. There was a slight deflection with a very few of the alpha particles, maybe 1% or 2% deflection, but the vast majority were going straight through. He thought that probably due to the fact that, well, it was going through a solid material, and that material had positive charge. So there was some effect on the positively charged alpha particles. There was some small deflection. And he had also done this experiment with several other less dense metals, getting the same result, that the alpha particles primarily went straight through. But after observing the same thing with gold foil, he told his assistants, Geiger and Marsden, to go ahead and explore this further, to see if they could set up an experiment to find out if there were deflections that were wider than 1 or 2%. Why he told them to do this is a little bit of a mystery. Perhaps he was just an incredibly intuitive scientist. But they went ahead and set up the experiment the way it was seen at the beginning of the video. What they found was that once in a great while, very small percentage of the time, they would see a particle deflected much more than 1 or 2 degrees, even up to 90 degrees away from going straight through. But what was even more astounding is maybe 1 out of 20,000 alpha particles would actually bounce back. They were trying to come up with a model of the atom that could explain these very strange results. In a famous quote after these results, Rutherford said that it was like shooting a cannonball at tissue paper and having the cannonball bounce back at you, and that goes to his understanding of the alpha particles as being incredibly dense, fast-moving particles being shot at a very thin, much less dense material. And so here's another view. Many particles almost all going straight through, once in a while being either deflected or bouncing straight back. And that's what the Geiger-Marsden team was looking at. Almost every one of the particles just going straight through or very slightly deflected, a very, very tiny amount deflected, and even tinier amount, 1 out of 20,000 deflected, more than 90 degrees. So the model they came up with, in order for the alpha particle to bounce back, the majority of the mass of the gold atom must be kept in a very, very tiny part of the atom, and therefore leaving the rest of the atom as empty space. So if the mass of the gold atom is in a very tiny part of the atom, that would make it a very, very dense particle. And it would have to be extremely dense in order for it to be able to bounce back an alpha particle. And this very dense nucleus, as Rutherford did call it, would also carry the positive charge, and that would explain deflections of alpha particles passing close by. So if the vast majority of the atom is empty space, that would explain most of the particles going straight through. But once in a while, knowing that the alpha particles are positively charged, if the nucleus also contains the positive charge of the atom, if the alpha particle came close enough to the nucleus, it would then be deflected greater than a couple of degrees. Something more like that. And if the nucleus was really that small, that would account for the fact that such a small amount of the alpha particles would be deflecting back. They would have to collide almost head on with the very, very tiny nucleus to bounce backward. So most particles would pass straight through, a few deflecting greater than 1 or 2%, and then even smaller amount of time deflecting backward. I think what's incredible about Rutherford's conclusion is the radical nature of it. To say to the world that atoms are mostly empty space was quite a bold move, and in fact the scientific community did not readily accept it until a couple years later, when Moseley, who was also working with Rutherford, came along and basically independently verified, using a different approach, verified the results that Rutherford got. But what's even more interesting about this, if you think about how the structure of the atom eventually developed over the next 15 years, the behavior of the electron needs a lot of space in order to move around in to satisfy what quantum mechanics came up with. And so the discovery of the nucleus, making the atom mostly empty space, provided for the electrons to have space to do what eventually they were discovered to be doing, using Bohr's criteria of electrons existing at varying distances from the nucleus depending on their energy, and Heisenberg's ideas and Schrödinger's ideas of the electrons moving in undefined paths in probability clouds within the atom. So a couple of last points. So he found the nucleus and all the empty space that was in the atom, but he had to figure out what to do with the electrons. And he came up with the planetary model that the electrons are orbiting the nucleus. But he realized this was not a very good model. There were a lot of problems with it. And in fact, he figured out with such a strong attraction between the negative electrons and the positive nucleus that it would actually take about 10 to the negative 9 seconds for the electron to spiral into and crash into the nucleus as it was orbiting the nucleus. So he knew the model had problems, yet he and Bohr and many others held on to that planetary model for lack of a better model until de Broglie, Schrödinger, and Heisenberg came along in the next decade, the 1920s. And finally, another very important point was that Rutherford was actually able to determine the approximate size of the gold nucleus simply by comparing how often the alpha particles were deflected versus going straight through. And his calculation put him very close to what we know is the actual size of the gold nucleus. So even though Rutherford had already won a Nobel Prize before even doing any of these experiments, his Nobel Prize for radioactivity allowed him to gain an understanding of the type of particles that he was using, and therefore allowed him to understand what structure the atom must have in order to result in the observations that he eventually saw with the gold foil experiment.